Good morning, everyone, and thank you for joining today's session. The topic of this presentation is about transitioning Unity app games into mini-games. Last year, we worked with several teams on transitioning Unity games to mini-games, during which we encountered a number of challenges and developed solutions. Today, I'll be sharing our insights and experiences. First, we'll explore the memory structure of minigames, followed by a discussion on how to convert synchronous operations into asynchronous ones. Next, we'll address some unique challenges encountered on iOS, and finally, we'll look at various optimization techniques. Let's begin with the first topic, memory structure analysis. This pie chart comes from the official documentation of WeChat minigames. To be honest, when we first saw this chart, we were somewhat confused, as its memory structure is quite different from that of Unity app games. It took us a while to figure out the meaning behind this chart. One important note in the official documentation is that dynamic memory is the sum of three components. Among these three components, native reserved differs from Unity's native or Unity reserved. Moving forward, we will analyze various resources such as AssetBundle, textures, meshes, animations, audio, RenderTexture, mono, etc., and correlate them with our test data to provide a clearer understanding of these concepts. Many development teams are not fully familiar with the composition of memory, and we also spent considerable time figuring out the details. Our primary focus has been that minigame memory on Android platforms doesn't often cause crashes, but on iOS, memory issues frequently lead to crashes. Therefore, we will focus on iOS in this presentation. On iOS, crashes typically occur when the minigame memory reaches 1.3 gigabytes or 1.4 gigabytes. Specifically, when connecting a WeChat minigame to Xcode, you'll notice two processes, one called WeChat and the other WebKit.WebContent. We'll refer to the former as the WeChat process and the latter as the WebProcess. Crashes mainly occur when the WebProcess exceeds 1.3 gigabytes or 1.4 gigabytes of memory. To test this, we packaged 100 different images, each 21.3 megabytes, 2048 by 2048, uncompressed, with read-write enabled, into an asset bundle and sequentially loaded them into memory. We observed that the WeChat process memory grew by about 2.1 gigabytes, while the web process memory only increased slightly. The increase in memory was primarily observed in the WeChat process when loading textures. Thus, when only textures are loaded, web process memory doesn't increase much, and the minigame doesn't crash. Crashes are typically caused by the web process memory exceeding the 1.3 gigabytes or 1.4 gigabytes limit. We further analyzed the loading of resources like AssetBundle. We loaded 21 asset bundles, totaling about 200 megabytes. Using Unity's native interface, we saw that native reserved memory increased by about 200 megabytes. Dynamic memory increased by roughly the same amount, and the web process memory also increased, while WeChat memory remained nearly unchanged. From these tests, we found that regardless of whether we use Unity's native interface or WeChat AB interface to load asset bundles, both methods impact web process memory, affecting the stability of the minigame. Therefore, we recommend using the WeChat AB interface to load resources. In addition to supporting timely unloading, it also has cache management capabilities, which can be further explored in the official WeChat documentation. Earlier, we discussed how loading asset bundles might affect minigame crashes, especially the content within the asset bundles. To optimize this, we aim to maximize the utilization of loaded asset bundles to ensure resources are used efficiently and avoid waste. To achieve this, we developed a tool that tracks which resources within a loaded asset bundle are actually used. For example, during a specific testing period, the tool reports which resources were loaded and actively used. By analyzing reference count data, we can distinguish between actively loaded and passively loaded resources, calculating the actual usage percentage of each asset bundle. We found that the actual utilization of many asset bundles was low, even below 10%. For these low utilization asset bundles, we further analyzed the larger resources within them to understand why they occupied so much memory without being effectively used. Our strategy is to prioritize optimizing these high memory consuming but underused resources. For this, we used Unity's built-in web extract and binary-to-text tools to extract detailed information from the asset bundles and analyze the loading and referencing relationships. This allowed us to compile a clear statistical table that supports our optimization efforts for AssetBundle memory usage. Next, let's look at texture handling. As previously mentioned, one of the reasons for iOS crashes is that when texture resources are not set to read-write (RW), they are entirely loaded into the WeChat process, which causes the majority of memory usage to be in the WeChat process. When texture resources are set to RW, their memory management is different, with part of the resource existing in both the CPU and GPU. In our tests, we loaded a texture asset bundle using the native method and found that the memory usage of the texture AB increased by 13 megabytes. Native reserved memory increased, while dynamic memory grew by approximately twice that amount, to about 25 megabytes. This pattern was consistent across multiple test cases. Next, we loaded textures with RW enabled. For each set of 10 textures loaded, memory usage increased by about 213 megabytes. We can see that with RW enabled, memory is allocated to both the CPU and GPU, much like resource management in an app. The CPU part corresponds to the web process, while the GPU part corresponds to the WeChat process. Therefore, enabling RW for textures in WeChat minigames can affect memory usage and potentially lead to crashes. Now let's discuss mesh handling. Mesh memory management is similar to texture memory management. When mesh resources are set to RW, they exist in both the CPU and GPU. After loading the mesh asset bundle, native memory increased by 33 megabytes, while dynamic memory and web process memory both increased by twice that amount, approximately 66 megabytes. This increase is due to reserved memory. In further tests, when we loaded 10 meshes, native reserved memory increased by 50 megabytes, approximately 5 megabytes per mesh, while dynamic memory increased by 31 megabytes and the web process increased by 30 megabytes. This is because the previously mentioned 33 megabytes of reserved memory allowed new meshes to occupy this space, preventing the memory increase from reaching 50 megabytes. Animation resources don't have an RW option. After loading the animation asset bundle, native reserved memory increased by 80 megabytes, while dynamic memory and web process memory both increased by 160 megabytes. The 80 megabytes increase can be attributed to the reserved memory, which allowed space for subsequent resources. When we loaded 10 animation resources, native reserved memory increased by approximately 55 megabytes, with dynamic memory and web process memory increasing by the same amount. This is because the reserved memory was sufficient to accommodate the new resources, preventing an excessive increase in total memory usage. In conclusion, animation resources directly affect minigame memory usage, particularly in the web process. By effectively managing reserved memory, we can reduce fluctuations in memory growth and avoid stability issues. Now let's analyze the impact of audio on memory. Audio exhibits a peculiar behavior. After loading the audio asset bundle into memory, we observed memory usage that resembled reserved memory behavior. Specifically, the loaded AB package was large, with native reserved memory increasing by 130 megabytes and dynamic memory and web process memory increasing by about twice that amount, to 207 megabytes. Strangely, when we loaded the audio, the first three memory values remained unchanged, but the last value, WeChat process memory, spiked. Over time, this spike would gradually decrease. When we continued loading audio, each additional file increased memory by about 7 megabytes, with all the increases concentrated in the WeChat process, not directly affecting minigame crashes. Although the increase in audio memory doesn't directly cause crashes, audio compression is still necessary for optimizing memory. According to WeChat's official recommendations, audio files should be converted from stereo to mono, as left and right channels are often identical. Converting to mono significantly reduces memory usage. Additionally, setting the audio quality parameter to 1, as opposed to 100, yields a large reduction in memory usage with almost no perceptible difference in quality. After optimization, the size of the asset bundle decreased significantly. For example, a set of 20 audio files originally had an asset bundle size of 137 megabytes, which was reduced to 68 megabytes. As asset bundle size directly impacts web process memory usage, optimizing audio file size can reduce web process memory consumption, thus decreasing the risk of crashes. Therefore, although the size of audio memory does not directly cause crashes, optimizing audio files is essential. The official WeChat recommendations for optimization are highly effective in reducing memory usage. Let's now analyze the impact of mono on memory. Reviewing previous steps, we loaded a texture asset bundle, then completely unloaded it. After loading, dynamic memory increased to 292 megabytes and web process memory increased to 733 megabytes. After unloading, native reserved memory decreased, but the other two memory categories, dynamic memory and web process memory, remained unchanged. Next, we allocated a 20 megabytes integer array, and we observed that mono memory increased by 20 megabytes. Both dynamic memory and web process memory increased by around 20 megabytes as well. Based on earlier formulas, dynamic memory equals mono heap plus native reserved. When we allocate the 20 megabyte array, mono memory increases without affecting native reserved memory, showing that they are independent. However, mono memory increases directly impact dynamic memory and web process memory, which can lead to instability and potential crashes. Later, we reloaded the 200 megabyte asset bundle we previously unloaded. Upon reloading, dynamic memory and web process memory did not increase, as the previously allocated reserved memory could still accommodate the new resources, keeping memory growth stable. This test shows that monoheap and native reserved memory are entirely independent, and the reserved memory can be reused without being affected by mono memory allocation. Therefore, managing reserved memory is crucial for preventing crashes. Next, let's look at the memory impact of RenderTexture. We created several 2048 render textures using a 24-bit depth buffer and RGB32 format. Each render texture consumed about 32 megabytes of memory. After assigning them to a camera and actually rendering with them, so these were genuinely in use, not just allocated, we monitored the memory changes. What we found was interesting. The memory increase had almost no impact on the web process. Instead, the growth was concentrated in the WeChat process. Each render texture increased memory usage by roughly 37 MB, but it did not contribute to minigame crashes. This suggests that render texture memory, at least under these conditions, does not significantly affect overall stability. That result was somewhat unexpected. Based on all of our testing, we summarized the memory model of WeChat minigames on iOS. At a high level, there are two major processes, the web process and the WeChat process. They occupy separate memory spaces. For textures, if read-write RW is disabled, textures go entirely into the WeChat process. If RW is enabled, part of the texture memory is allocated into native reserved. Render textures and audio resources also go directly into the WeChat process, meaning they do not directly trigger crashes. Again, this was not what we initially expected. So what actually drives crashes? There are three major components that impact minigame crashes: Unity Heap WASM Canvas and the base runtime libraries. Unity Heap is configured in the WeChat minigame conversion plugin. Its size must be carefully tuned, not too large and not too small. If it's too small, dynamic memory will force reallocations, leading to heap expansion. That reallocation process itself can cause instability. The best practice is to run multiple profiling sessions, observe your actual dynamic memory usage, and set Unity Heap slightly above that level to avoid repeated resizing. Dynamic memory consists of three main parts: monoheap, native reserved plugins, such as Lua. Inside native reserved, we observed native asset bundles are allocated here. Animations directly increase native usage. Textures and meshes with RW enabled allocate a copy here. Built-in Unity native resources such as fonts, shaders, and particle systems also consume native reserved memory. Another significant contributor is the IL2 CPP runtime. According to official documentation, optimizations have been made to reduce its native reserved footprint. We did not perform in-depth analysis on Lua plugin memory usage. WASM is another critical factor affecting crashes. Enabling WASM Split can significantly reduce memory usage. In one project we tested, without WASM Split, the web process consumed around 700 megabytes upon entering the game. With WASM Split enabled, it dropped to around 500 megabytes. That's a substantial difference. The actual reduction depends on your codebase size, but enabling WASM Split is strongly recommended. Canvas and the base libraries represent unavoidable overhead. This is foundational runtime cost and cannot be eliminated. What we can control is Unity Heap and code size. Removing unused code and enabling WASM Split are effective strategies to reduce memory pressure and improve stability. We also tested TikTok mini games and found that its memory model differs significantly from WeChat. In TikTok mini games, textures and meshes always go directly into the web content process, regardless of whether RW is enabled. We did not observe a separate process like WeChat's GPU side process. Because of this, TikTok mini games are generally more prone to crashes compared to WeChat. For audio and render texture in TikTok, we were not able to identify a consistent memory pattern. To conclude, regardless of whether you are targeting WeChat or TikTok mini games, optimization is still necessary. Even if certain resources like textures do not directly cause crashes in some cases, excessive memory usage still increases asset bundle size, impacts loading time, and degrades overall performance. Stability is only one part of the equation. Memory efficiency affects the entire user experience.